We are Team 1028 from Utah Tech University, and we will be looking at Problem A, sweet tooth and heavy metal. No, not that kind of heavy metal. We will be looking at these heavy metals: lead, cadmium, and arsenic. Recent studies have shown that many chocolate products contain heavy metals such as lead, cadmium, and arsenic. These heavy metals are part of a list of chemicals the World Health Organization deems as a public concern. This is because the accumulation of these metals in one's body can lead to serious health effects. Our goal is to model the accumulation of these metals in a person that regularly consumes chocolate. We are considering varying levels of chocolate consumption and want to find out if increased chocolate consumption around the holidays has an effect on the accumulation of these heavy metals. Before getting into the model, I want to take a look at the assumptions we will be making. First off, we will assume the only source of heavy metals for a person is chocolate. We will also be assuming each heavy metal has a whole body half-life, and we are basing that off where the metal primarily accumulates in the body. For example, lead mostly accumulates in the bones, so we are using the half-life of lead in bones. Another assumption is that the absorption rates, amount per serving of chocolate, and half-life of these metals do not change throughout time. We will be starting the model at age 2 years old and simulate the accumulation over a person's whole lifetime, so to about the age of 80. We are also saying that the average chocolate consumption throughout the years of their life will be the same, but the consumption around the holidays will vary with age. So now taking a look at how we constructed our model, we have a system of differential equations for each heavy metal. Each equation takes into account the absorption rate of the metal, or how much of the ingested metal actually gets absorbed into the body, along with the amount of metal per serving of chocolate and the number of servings of chocolate at any given time. Each equation also takes into account the assumed whole body half-life of that metal. Now taking a look at the parameters we used in the differential equations, we see that the absorption rate for each metal varies quite a bit. Also, we see that one serving of chocolate has about 4 times as much cadmium compared to lead and arsenic. I want to point out that the half-life of arsenic is significantly less than the half-lives of lead and cadmium. For this reason, most of our scenarios looking at long-term accumulation will only include lead and cadmium, and later we will take a look at a certain short-term scenario for the accumulation of arsenic.
For chocolate consumption rates, we referenced a study on candy consumption patterns, which found that 15% of Americans over the age of 2 consumed chocolate on a given day. Although children had higher consumption rates of candy in general, the chocolate consumption patterns specifically stayed very similar. Assuming that on any given day an average person has a 15% chance of consuming chocolate, we determined that the average person will eat chocolate about once a week. This stays consistent from children to adults. Where we will see them differ will be around the holidays, where adults are more moderate compared to children in their consumption of chocolate. For both age groups, our base case will assume that they will spread out their consumption around the holidays with increased candy consumption. The holidays we consider for increased candy consumption will be Halloween, Christmas, Valentine's Day, Easter, and the consumer's birthday. We did not find that the time of year of the consumer's birthday had a significant impact on the long-term trends, so we will present our results with an arbitrary birthday of June 19th, noting that changes could be present if considering the short-term rather than the long-term accumulation. Our first scenario will serve as the average chocolate consumer with the assumptions that we have laid out. We see that during an average week, the consumer will have 1 serving of chocolate. For consumers aged 2 through 20, they will reach a maximum of 5 servings during the holidays, and age 20 plus will reach a maximum of 3 servings during the holidays. We considered how chocolate consumption would be spread out around each of the holidays, and the behavior is specific to each. For example, Halloween and Christmas are associated with higher levels of chocolate consumption since the average supply of chocolate would be greater, and therefore is spread out longer so the consumer would have a higher level of consumption for a long period during those holidays. The accumulation results for heavy metals, lead and cadmium, can be observed on the graph. We see bumps on the graph during the holiday, and as they become more moderate as adults, the metal accumulation begins to slow. At age 80, we observe lead at around 1,500 micrograms and cadmium at about 1,150 micrograms. Compare these to our noted average total body burdens of these metals, we see cadmium increases from around 9,500 to 50,000 micrograms over the life, and the average adult human has about 153,000 micrograms of lead in their body. This tells us for the average adult, these are not key contributors to the total heavy metals in their body. Although research has noted no safe levels of lead and possible unfavorable side effects of consuming heavy metals, the average person would not be greatly affected by the metals found in chocolate under average consumption, and it would not accumulate to a threatening level.
In scenario 2, representing low chocolate consumption, both age groups consume chocolate only occasionally. On an average day, neither group consumes any chocolate. However, during special occasions such as holidays or birthdays, the consumption is halved from the average consumption. The overall shape of the accumulation graph in this scenario remains similar to scenario 1. However, by the end of 80 years, the total lead accumulation reaches approximately 520 micrograms, while the total cadmium accumulation is just under 400 micrograms. This is a significant reduction in total heavy metal accumulation compared to scenario 1. In scenario 3, which represents high chocolate consumption, both age groups consume chocolate much more frequently than in the previous two scenarios. On an average day, individuals in both age groups consume 1 serving of chocolate. During the holidays and birthdays, consumption was doubled from the average consumption. As in the previous scenarios, the accumulation graph for both lead and cadmium follows the same general shape. However, the final accumulation values after 80 years differ significantly from those in the low and average consumption scenarios. By age 80, the total accumulation of lead is around 5,500 micrograms or 5.5 milligrams, while cadmium reaches just under 4,000 micrograms or close to 4 milligrams. Compared to the last two scenarios, the total accumulation of both metals is vastly higher. In scenario 4, we explored a holiday binge pattern. In this case, both age groups maintain an average chocolate consumption rate of 1 serving per week. However, unlike previous scenarios, all chocolate received for holidays is consumed in a single day rather than spread out over time. This leads to significantly higher consumption on holiday occasions. Just as in all previous scenarios, the holiday binge pattern does not change the overall shape of the accumulation graph. By the end of 80 years, the total lead accumulation is just under 1,500 micrograms or 1.5 milligrams, while cadmium accumulation is slightly over 1,000 micrograms or 1 milligram. Compared to scenario 1, where holiday consumption is spread out, the binge approach surprisingly results in lower overall accumulation of both lead and cadmium by the end of 80 years. Since arsenic does not accumulate over long periods due to its short half-life of around 10 hours, we focused on a brief 10-hour period of high consumption similar to the holiday binge scenario. In this case, large amounts of chocolate were consumed. Over a total span of 50 hours, arsenic levels peaked at around 27 micrograms, but by the end of the 50 hours, less than 5 micrograms remained.
From each of the 4 scenarios, we have seen that chocolate consumption alone does not meaningfully contribute to dangerously high levels of heavy metal accumulation. This insight gained from the model is especially true for arsenic. This is because, as has been stated, arsenic has an incredibly low half-life. Additionally, scenario 4 suggests that while end-of-life levels differ somewhat, holiday binging has little effect on the total body burden of heavy metals with respect to toxicity. These scenarios also suggest that the largest contributor to chocolate-based heavy metal accumulation appears to be the rate of chocolate consumption. These suggestions are not to say that a chocolate consumer is completely safe, however. There are many other sources that contribute to the total body accumulation of heavy metals. These sources include other foods and drinks, industrial and occupational sources, medications, and tobacco smoke. Heavy metal-based toxicity has been shown to cause or contribute to a host of ailments. We must take precautions to avoid the overaccumulation of heavy metals within our bodies. The strength of our model lies with giving an overall picture of the total body burden of heavy metals in the body. Additionally, the dynamic nature of the model allows for the adjustment or updating of model parameters to more accurately reflect different situations. In addition to the strengths, we have identified weaknesses of our model. These weaknesses are that the metal accumulation is not separated into discrete compartments, and our model does not consider any other sources of heavy metal exposure. Future work on this problem could include building a more fine-grained model, including other bodily systems and their respective biological half-lives. Additionally, we would like to consider other sources of heavy metal exposure and the shorter-term effects of this overexposure. We would also like to research the possibility of biological half-lives being variable based on a variety of factors, including being proportional to the levels of heavy metals in the system or pre-existing conditions. Lastly, we would like to thank Vinodh for this modeling opportunity, MathWorks for graciously supplying us with a copy of MATLAB, and our faculty mentor, Dr. Vinodh Chellamuthu.